section. His research mainly focuses on investigating how human and natural systems respond to the world's changing climate and how human activities in turn impact back on the climate system. So he's been central to the development of the model and running the model in CMIP 6, CMIP 5, and now is doing CMIP 7 land cover and land use representations for CESM. He has a PhD from the University of Queensland in Brisbane, Australia, and a BS from Australian National University in Canberra, Australia. I've been practicing those. So I'm going to hand it off to Peter, but just a quick reminder, seminar will run for about 45 minutes. Afterwards, we'll transition to question and answer discussion. If you're online, if somebody can, oh wait, it's YouTube, right? Not Zoom? Okay, well hopefully online everything's working fine. If not, you can message me on GChat and we can fix any sort of issues that there might be. But we will use Slido if you're online for questions and comments at the end, and you should have a link on the YouTube page. So, Peter.
Thank you, Monica. Yes, so this is great to be here. I haven't given a seminar for a long time, so I'm really happy to see everyone's faces here, like post-COVID, it's really lovely. What I'm going to be doing today is going through a number of different projects I've been working on using CSM2 rather than CSM3, which a lot of people are working on right now to get that going. And this is making it in an emission-driven sense so that we are trying to understand the carbon cycle, understand how the carbon climate system is coupled, but also how human actions within that system influence the projections and the trajectory that the climate system will be taking. Obviously, this work involves a lot of other people, so I put some co-authors in here, but there are a lot of others. So like Dave, who's obviously been really important, Simone Tellums, Andrea Smith, Monica, and then some collaborators we have from the Arizona State University, Michael Barton, Cheryl Harrison, who spends a lot of time here at NCAR. She's at Louisiana State, and Tiger Felgenhauer, who's at Duke University. Okay. So what I really want to do is give you an outline of what I'm going to talk about today. And just so you get some sort of background, I wanted to start off with some motivation for why we need emission-driven modeling for understanding climate change, impact assessment, mitigation, intervention, types of activities to provide guidance on those. I then wanted to go through and sort of talk about developing CSM 215, which is the version of the model we're using, which runs directly in an emission-driven space. One of the things that we've done is we've added active fire and biogenic aerosols, and that actually ends up being a big impact on the climate system. So I'm going to spend some time taking you through that. Talk about the pre-industrial control and the historical ensemble of simulations, and do an evaluation against the large ensemble too. Then I'm going to go into a couple of projects. One of them is this highly optimistic projection ensembles, or HOPE. And this is looking at SSP 119, which is a scenario that we've never really explored with CSM before because we didn't have forcing data sets. And it's the most optimistic of the SSPs from CMIP 6, and it actually allows us to do overshoot and return back to current day temperatures and see how our model responds in that space. Then I'll go on to the Community Climate Intervention Strategies project, which we've been working here and with our partners that I introduced before. And then finally look at ongoing CMIP 7, Scenario MIP, CDR MIP, TIP MIP, and then some World Climate Research Program activities looking at climate interventions and tipping points. Okay, just to start off the context, I want to put it into sort of like the larger idea of what's happening in terms of international agreements, the United Nations Framework Convention on Climate Change, which is currently having its COP meeting in Baku right now, and give an idea of where we are in terms of looking at meeting the Paris agreements, the Paris targets of 1.5 and 2 degrees. And this is coming out of the sixth assessment report, and the blue line at the bottom is a 1.5 emission trajectory that would allow you to meet the Paris target. The green lines are 2, and the orange one is basically the nationally determined contributions that we currently have agreed to. If you look over to the far right on this slide, you can, sorry, here we go. Over here, we can see where we're going in terms of, this was last year's emissions. We were currently at 57 gigatons of CO2 equivalent. You can see that breakdown between the different sectors. And if we really wanted to be on, for 2025, on a 1.5 degree, we would be here. But this is currently saying we're at 57 gigatons, which is putting us over the orange line. So we're actually over a 2.8 to 3.1 degree warming trajectory right now. We can also look at seeing, well, what would it take to get back to those blue and green targets? And this is what's called the emission gap. And we can see that actually if we continue on this pathway we're on right now, by the year 2030, we will be up to 22 gigatons of carbon, which is basically half of the carbon we're emitting. We will be over emitting to hit that 1.5 degree target. And by 2035, it gets even worse. It's up to 29 gigatons of carbon. Okay. That's just a little bit of background. I think everyone knows about, like, yes, climate is changing. We're seeing larger impacts, but the actual impacts turn into dollar amounts. And NOAA does a really good job of keeping track of that. And you can see that, and this is all CPI adjusted to current day numbers. And you can see that 2017 was the highest one where we had like $395 billion worth of damages in that year alone. We had 3 major hurricanes, we had wildfires, we had droughts. And you can see that, like, this is way outside of like the historical expectations of where we should be. And as all of these years here are like we've got 2005, which was Katrina, but besides that, we're basically experiencing these damages. Big part of that is, like, we're seeing this intensification of storm systems. We've got Hurricane Milton here, which intensified in 48 hours from tropical storm to Category 5 hurricane. This is a bomb cyclone that's currently like just developed off the west coast of the US, which has got an atmospheric river associated with it. We're seeing this massive intensification of storm systems, and they translate along with background climate change into real damages. We're sort of seeing things like fires in the Amazon, drought in the Amazon. We're seeing wildfires in Canada. We're seeing massive coral bleaching events, large-scale glacial retreat and melting. We're seeing crop failures and large-scale flooding and damages. So we're basically in a space now that we should really be taking consideration about the path we're on. Okay, sorry. The other side of it, and this is the idea of there are tipping points within the system. So you continually push the system until the stability of the system, the background ecosystems and larger scale processes such as AMOC suddenly go into places where they're non-reversible. So we have the idea of that you get a threshold and you meet that threshold. And then they have feedbacks on both the climate system and the carbon cycle. So here we can see some classic examples. And then the idea is that sometimes these might impact each other as well. So like, as you see a breakdown in the Amazon, you will see large-scale carbon releases, which will be further adding to the climate. Will Stefan, who was an Australian researcher who we worked very closely with, who unfortunately passed away 2 years ago, he had this really seminal paper about the idea that the climate system has been in a very stable sort of glacial, interglacial sort of cycle for the last million years. If you think from the mid to late Pleistocene, we're in this period of glacial, interglacial, sort of going backwards and forwards. And the idea is that, like, driven by orbital cycles and radiation and then feedbacks in the ice and carbon cycle, we flip between these two states. But once we hit the Anthropocene, we're changing CO2 to the point where we could be impacting the systems that give those feedbacks, such as the cryosphere or the biosphere, such that we end up in a new world, which is very different from the one that we experienced over the last million years. And to think about the last million years as where humans basically came into existence, civilization was created, where we are right now. Okay, so that brings me to the second part of the talk, and start thinking about, well, what tools do we have available to help us guide through and answer some of these challenging questions? And I've got here the NCAR's community Earth system model. This is like, the release 2.15 version of the model, which has got all of these incredibly complex processes built into it, which is fabulous. So we can see the full carbon cycle can be like simulated. We can do volatile organics and fire aerosols. We can do agriculture, industry, and we represent the atmospheric process and everything that's responding to that. So we're using that as our framework for the community climate intervention strategies ensemble, but we're also using it for this HOPE project and be applying it for TIPMIP. So this configuration of the model allows us to ask really important questions. This is a little bit about the configuration of what we've got. So CSM 2.1.5 in this has fossil fuel CO2 emissions, has these aerosols that are actively being generated by fires, and the Megan biogenic volatile organic model, which is part of the land model. We also can now prescribe within this different forcings, so we can tell the model, this is what the fossil fuel emission trajectory looks like. This is where land use occurs. This is different actions that are going to happen within the Earth system model. We let the model run, and then we can interpret and do some impact analysis. And what's really nice is that CSM actually has embedded impact model. So we have an agricultural model through, just move that off the screen, sorry. So we have an impact model through CLM crop model, allows us to model. Currently we have 8 crops that are actively modeled, but we have 32 different crops that are represented in that model in terms of where they are. So they have the ability to model different types of corn, wheat, soybeans, cotton, sugarcane. We also have the fisheries model here, which is the feisty model that comes out of our new ocean biogeochemistry. So we can understand, we can simulate and try and evaluate different climate impacts beyond just basic biogeochemistry. We can go. We can also look at water availability and irrigation demand through both the crop model and also all the hydrological process going into the land surface model. We do wood production, and we look at ecosystem health. Okay. Right. So how do you go about configuring a model? It's like, I've done a lot of high-level conceptual, like this is the ideas of what's going on. But what I'm going to do is just explain to you how you go about running the model in this configuration. So we've expanded it to allow the active fires and biogenic aerosols. These were features that were built into the MAM4 model to start with. But instead of prescribing them from files, we're allowing the active models to set those emissions into the MAM model, the multi-model aerosol model. You can activate the CO2 simply by using the create new case. And Keith Lindsay and others have done an amazing job of setting up these comp sets. So if you use any of these comp sets, you can do an 1850 with, you can have it so the biosphere and both the radiation are both prognostic in terms of like, they're both seeing the tracer CO2 rather than the prescribed CO2 concentrations. And they can work for both 1850, the historicals, and also for the suite of SSPs, the 5 SSPs that we have like for CMIP6. The fire model and Megan can be turned on through can be turned on by just setting the CLM build ops. And then you define emission factors for both of those. They can be tuned and changed depending on how the aerosol model is responding. We have this new 4P, which is 4 producers and 2 zooplanktons, ocean biogeochemistry. You can just turn that on through this other nameless switch. And then what we did is took that configuration model and we've spun it up for 150 years from existing initial condition files, and it came into balance, and it's actually worked out to be a really, really useful model. There were a few things that sort of like tripped us up along the way. One of them was we had to reduce down from default values to get CMIP6 forcing equivalent aerosol burdens. That was important because the MAM model and the radiation model expect a certain aerosol burden. So if you put out just the raw numbers that came out of both the fire model and the volatile organics model, you put too many aerosols and you had this strong cooling in the model. So we had to reduce down those emission factors. We also found that there was this still rest time, top of model imbalance of around about half a watt per meter squared. So we reduced down the club C8 parameter, which affects the shallow cumulus clouds, the marine stratocumulus decks. I think that's a lot of work's been done on that. As a tuning in, thanks to Cecile, who gave me the guidance on how to do that. And then from this model that we've sort of tuned up, we now have 5 historical ensemble members that we've started off from different years within the pre-industrial control. And then from those historical simulations, then we have 5 ensemble members for each of these SSPs, the 119, which is this very aggressive mitigation scenario, 245 kind of business as usual, and 370, which is like a high warming scenario. The 370 is also our large ensemble 2 future projection. We're doing after doing the HOPE ensemble, we're now looking at individual climate interventions to try and do attribution, say, how much does afforestation do? How much does bioenergy do? And see if we can do that, sector by sector analysis. And finally, we're doing this all against the Lens 2 simulation with the smooth biomass burning. So that gives us a really nice target to work out how impactful this model configuration is. Okay, so what I'll do is I'll just start by thinking about what does the model look like in terms of global surface temperature, global average surface temperature. On the left, we have this new configuration. On the right, we have Lens 2. The black line is HAD Crew 5. What we see is the model has very similar spatial patterns in terms of warming. We have slightly more warming. We start off cooler in the model in 1850, and we end up at a point that's just slightly cooler than the large ensemble 2 in 2014. We can see that the model itself has more warming. I guess that's probably the easiest way to do it. Doesn't kind of work. Yeah, there we go. So there has more warming through the Central Pacific, the Atlantic, across the oceans. We have slightly more warming in the Southern Hemisphere. Okay, so trying to understand why the model is doing this. And so what I've done here is looked at the new configuration model, which I'm calling CCIS, against Lens 2. This is 5 ensemble members from Lens 2 because we're doing a 5-to-5 comparison. And what we can see is that in 1850, the model is cooler in the Southern Hemisphere, extensively cooler in the Southern Hemisphere, but it is warmer across sort of North America and then in the North Pacific. When you look at current day, the cooling in the Southern Hemisphere relative to Lens is smaller. So because the model warmed more, we have a smaller difference in 2014 than we did in 1850. Okay. So the question is, well, what's driving this? Is it CO2? Is it aerosols? So we started sort of like probing into that. And one of the things about, because we've tuned the model up really nicely for CO2, we actually track CO2 almost perfectly from the ocean and the land sinks and the emissions and the land use. So we've done a pretty good job of that. So we don't think that this is essentially a difference between having active CO2 and having prescribed CO2. But there are quite big differences in global aerosols. But the thing is that the new active aerosols are lower in 1850 than the Lens. So that was sort of counterintuitive. You wouldn't think that if you have lower aerosols, you would have a colder planet. But it turns out it is lower globally. And this plot over here on the right shows the difference in aerosols between the active and Lens. And you can see that the Central Pacific, the South Atlantic, the Indian Ocean, all have higher aerosols relative to Lens. And so that's what's driving this cooling of the oceans. We also see that over land, we have much less aerosol burden, especially over like North Africa, India, and then down into Australia. It seems that the location of the difference in aerosols is a very strong driver in what's going on here. Okay. One of the really interesting things is if we compare it, and this is going back to the CSM2 paper, and against these sea surface temperature biases that are known to be, current day biases known to be in CSM2, these are actually reductions in some of the known temperature biases across the oceans in current day. Okay, so we can start thinking about, and this is, Adam, thank you so much for your climate variability package. This has been really fabulous to be able to use this. But delving into each of the different ensemble members and saying, and down the bottom left here, we have the GIST temp record. It runs from 1900 to 2022, so it's a slightly different period from 1850 to 2014. But what we can see on the right-hand side are all the new CCIS active warming runs versus what's happening here in Lens 2. And so we have stronger warming, which seems to be more consistent with what we're seeing in the GIST temperature record. I'll note there's a Nature paper out today saying that there is like questions about how cold it was in the early 20th century, but I won't go into that right now. Okay. So the next question is, what do these aerosols do to precipitation? And so here I'm doing a difference between CCIS, the fully coupled model, and Lens 2 in 1850 on the left, and in the early 21st century on the right. You can see that like the aerosols actually reduce precipitation in the Western Pacific strongly in 1850, and that difference between them decreases as you go through time and end up at the end of the 20th century, beginning of the 21st century. We don't see large-scale zonal changes in precipitation between the two models. They are very similar in terms of their model precipitation distributions. Okay, again, Adam, thank you so much for this. So we have the global precipitation climatology down here, the GPCP version of what we know precipitation to look like. And then we have the lens on the left again. And you can see that it has basically the same spatial patterns. These precipitation changes are actually, the decreases are in areas where we actually currently have strong precipitation high biases, so that was not necessarily a negative thing. Okay, and then what does it do in terms of precipitation change through the historical record? And what you can see on the left-hand side here is the new coupled version, and we get a slightly stronger increase in precipitation in the South Pacific convergence zone, the Western Pacific, than we do in lens 2 on the right-hand side. They're the same sort of spatial distribution. I think qualitatively, like they're very similar, but you can see that the aerosols do have an impact in terms of precipitation changes. And this is more the fact that those areas are drier in 1850 in the new version of the model than they are in the lens 2 model, which is a lot warmer model in 1850. Okay, this is just quickly just having a sort of breaking it down into the different components of this aerosol difference. And so what we can see if we look at black carbon versus secondary organic aerosols versus sulfates versus particulate organic matter, we pretty much, this tuning mechanism, this tuning activity we went through allowed us to hit these fairly closely. So it's not necessarily a big magnitude difference in these. There is actually quite strong differences in terms of variability, having an interactive fire model and interactive volatile organics that are responding to climate rather than being prescribed from a file that was generated for CMIP6. But we're generally in the same ballpark, so it's actually the spatial distributions that really matter in terms of the climate impacts. When we look at the carbon cycle, we can look at the global carbon cycle in terms of CO2 concentrations and the tracer that is actually in the model, and we do a much better job with a fully coupled model because the land sinks and the ocean sinks are responding more closely to the way we would expect them to respond. So the black lines here are the Global Carbon Project from 2022. You can see we have and for these fluxes, this is the accumulated amount. So this is how much the land has taken up or lost. Cumulative loss to the atmosphere. So it's a positive to the atmosphere. And so what we can see is that the land was losing more carbon than the Global Carbon Project. Let's see if we get this to work. So this blue line here was saying that we were kind of overshooting what the Global Carbon Project said in terms of loss of carbon to the atmosphere from the land. That's through land use and also it's mostly through land use. And then for the oceans, which are down here, this blue line, when we have an interactive carbon cycle, the ocean is responding in terms of like it's getting able to draw down the carbon that's in the atmosphere, and it actually allows it to draw down more carbon. Okay, that's something that's just an interesting fact of coming out of a fully coupled system. If we go into the land in more detail, and a lot of the things we didn't want to see big changes because we wanted to use this framework, and so we wanted to use lens 2 as a really nice, robust starting point. So we're really happy that we didn't change the model dramatically in this process. Total veg carbon is very similar. We have slightly more vegetation carbon with the interactive CO2. We have very similar air temperature for the land, very similar amount of gross primary productivity, latent heat fluxes, transpiration, canopy evaporation. They're all very similar. So we don't see large-scale changes by configuring the model in this way. Just quickly looking, so land use, because we're prescribing the land use, and I guess that's an important component, we tell the model where the trees are in this particular configuration of the model. We say, this forest is cut down, this forest is expanded, this agricultural area is used for this crop, and that changes every year. And so what you can see is that between the lens model and our version of the model, they have the same land use going on, and they have very similar fire properties. We haven't really altered a lot of the dynamics of the land model by configuring the model this way. Okay. So now I've given you sort of like a historical sort of like say, okay, this model kind of works, does some slightly different things, not sure whether they're better or worse, but they generally look like they're more consistent with some of the observational data we have. Let's think how we can use this framework and ask important questions. And so we started off with this plot on the left saying we're above this orange line. And the UNEP emissions gap report that came out 2 weeks ago says basically there are mitigation potentials built into different sectors. So if we were to transition energy, we could potentially be able to mitigate out 14.5 gigatons of CO2. Afforestation, reforestation, we could probably do another 12.8. So that each of these components could actually help us achieve moving from that orange line to the blue line. So we're running what's called the HOPE project. This is the highly optimistic projection ensembles. And it's basically saying, can we, with our model, achieve that blue line? And the SSP 119 was set up to be that blue line in the scenario MIP CMIP6 process. And we can compare that to 245 and 370, which are on these sort of orange or above orange pathways. Okay, so how do we go about doing that? Well, so the model in emission-driven space is driven by fossil fuel emissions and aircraft emissions. So that's the top left plot here. And you can see the historical period. This is the green line coming through here. We hit 2015, and we do this sort of four-way splice, which I've sort of put here. The blue line, dark blue line going down is SSP 119. And so what we see is by 2050, we've gone from positive emissions to negative emissions. So there is negative emissions built into this scenario. That's either through bioenergy with carbon capture and storage or some form of direct air capture. We can see that the middle line, the purple line, here we go, so I'll just do that. This purple line here is SSP 245. So we keep on emitting, but we get to about mid-century, we hit a peak amount of emissions at that point in time, and then we decline and go down. And then SSP 370, which is our strong warming scenario, is this yellow line. Oh, sorry, well, this is actually a process. Anyway, this is the yellow line that goes up, keeps going up. We have land use occurring at the same time, so that the SSP 119 has a large increase in forest area at the same time, and we reduce wood harvest, so we're no longer taking a lot of wood products out of the forests. Okay, so just to jump straight to the point, we can see the temperature profile on the top right, and then this is the CO2 on the bottom right. And you can see that the fully coupled model, this CESM configuration, actually reproduces CO2 trajectories for 370 really nicely. This is the bottom right one. 245, we actually have CO2 that's a little lower than the scenario MIP generated CO2 concentrations, but we're pretty close to that. And then this 119 is a CO2 trajectory that we didn't have forcing files for because that one was like an optional, not used scenario MIP sort of forcing set. So what you can see is that in SSP 119, yes, we continue to increase CO2 for a short period of time, but then we rapidly go into reducing CO2 concentrations. If you look at the top right-hand panel, you can see that there's a temperature response, and the temperature comes back down to like 2015, 2014 levels at the end of 2100. But there is a period of time where even all three scenarios are continuing to increase in temperature, even with this strong mitigation response. Okay. We can start looking at spatially what these different maps look like as well. So this is the change in temperature from the beginning, so the beginning of the 21st century through to the end for the SSPs, and the historical period in the top left-hand point. So the point is that, yes, we can do this overshoot with SSP 119, but we end up with this very strange sort of spatial distribution in terms of, so the global average temperature ends up back at around about 2014. But we end up with very cold North Atlantic, with very cold Arctic, and we also end up with like continued warming in the southern hemisphere through like the Pacific and the Southern Ocean in Antarctica. It's obviously nowhere near the warming we see in these two bottom panels, which is SSP 245 and 370. But we're seeing still major changes in the climate system that we would potentially not want to see happen, especially the North Atlantic. That's 6 degrees cooler than current day. I was going to say quickly, the aerosol burden as well, SSP 370 continues emitting, and we end up with this large aerosol burden that offsets some of the warming. SSP 119, even though we're doing large-scale reductions in CO2, we are cleaning the air in that process, and there is a warming response in terms of the aerosol CO2 feedback, which is why all three scenarios continue warming out to around 2035. So in terms of the political statement of, well, if you completely mitigate it and stopped emitting aerosols, you continue to see warming, that's going to be a difficult one to sort of like present. What I also wanted to say was this cooling in the North Atlantic is consistent across all of our scenarios. And Aishu gave a really good talk on this a few weeks back. What is the mechanism that's driving that? And you can see that it's actually not scenario dependent. So this plot here of AMOC shows the shutdown of the heat transport of the Gulf Stream into the North Atlantic. And basically it starts off, it slows down through a warming process, so it becomes less dense, it's more buoyant. But once that process stops, this model and pretty much all the CMIP6 models stop bringing salt in. And that salt is really one of the big drivers of the AMOC. So even though you're cooling in the North Atlantic, you can't restart AMOC just by cooling. It needs, we end up with, because you've shut down that transport of salt, you get this freshening in the North Atlantic, and it's really cold and fresh, which means it's still not dense enough to drive AMOC. Okay, and you can see that across all the scenarios, and you can see that at the end of the 21st century, when we return the temperatures back to current day, AMOC hasn't restarted. It's slowing down in terms of its rate of slowdown, but that's about it. We'd really need to project these out a lot further to see what the long-term response in our model is. And this isn't just a CSM response. This goes across all the CMIP6 models. Okay, and I guess Ashu's leading a tipping point component of that for TIPMIP. So one of the next things we want to try and understand is, well, what happens with precipitation in our model under these different scenarios? And you can see that that was the historical change in precipitation that we modeled. We saw this sort of shift in this. We get more rain in the Western Pacific and the South Pacific convergence zone. But we also see drying above the equator. When we go to SSP 119, where we've returned the world back to its current temperature average, we actually see there is still this very strong shift in the ITCZ. We've moved a lot of the precipitation to the Western Pacific. And what we can see if we look at the plot in terms of global precipitation is that even though temperatures have returned back to current day, we have higher rainfall rates in 2100 in that blue line in the top right panel. Obviously, that shift in the ITCZ south gets stronger the stronger the warming is. So you can see that 245 ends up with a bigger shift south than 119. And then again, same thing for 370. Aishu, in a couple weeks ago, put a lot of work into trying to understand what the mechanisms for that are. This differential cooling in the northern hemisphere versus warming in the southern hemisphere seems to be a major component of that. Okay, let's start looking at the carbon cycle. And so what we've got here are global amounts of land carbon, ocean carbon, also the fluxes. These are all fluxes. And so what you can see is that going through the historical period, we're drawing down carbon into the land, we're drawing carbon down into the oceans. So the blue line, the SSP 119, because we initially do all this reforestation, we draw down more carbon than the other simulations. But when we get to 2050, the CO2 concentration, the CO2 concentration is suddenly dropping. It doesn't matter. Oh. CO2 concentration is suddenly dropping, and the land sink no longer is as effective as the other SSPs. So we end up with a point where we get to the end of 2100, and our land sink is like a lot smaller than it was mid-century. And that's simply because the atmospheric CO2 has decreased. Same thing happens in the ocean fluxes. So as we're decreasing CO2 in the atmosphere, the amount of carbon that the ocean is taking up in SSP 119 decreases and decreases. And in fact, it's actually a slight outgassing of CO2 at the end of 2100. We can look at the GPP and the MPP fluxes on land. And we can see that they actually strongly respond across the CO2 concentrations in the right-hand plot. Okay, so that's to give you an idea of our model in this sort of scenario space. And that's sort of like just trying to evaluate these scenarios that were generated by CMIP6 and say, okay, yeah, our model can achieve some of these targeted climate responses through activities such as like reforestation or negative emissions. So what I'm going to do is now switch gears a little bit and talk about our Growing Convergence Research Award that we had awarded 2.5 years, or just 2 years ago now. Unfortunately, it's been awarded for 5 years, but we only got the first 2 years of funding, and NSF decided that they weren't going to fund the second phase, which is years 3 through 5. So this is now an unfunded project. But we did a lot of great work in these 2 years, and I just want to take you through that project. I see Will looking at me and saying, yeah, I know, I feel your pain. So I'll acknowledge like the people that I had as the co-authors are also the partners on this grant and this project. We built up a large set of collaborators with the World Wildlife Fund, the Nature Conservancy, UCAR Office of Government Relations, and we were building up a large stakeholder group because this is really about generating actionable research to investigate combined climate intervention strategies for stakeholder guidance. It was like, let's do some great research, but let's make sure that that guidance is responsive and epistemically like valid for, sorry, Monica like said I didn't say that. Epistemically responsible for giving guidance. So we know the limitation of our models. We know what we can say is valuable. We're not trying to give too much certainty in terms of activities or actions. And we're not being advocates in this process. What we're doing is we're really trying to drive the research so that it responds to the questions that are being asked by our stakeholder group. We built up this really great workflow with our partners. So we have this scenario generation. We were going through, we're doing baselines. We've done all the baselines. We've got these one by one climate interventions off a baseline control. And then we're building up this ensemble simulations into a data archive. We have these analysis toolkit that we were planning to build with this as well. We started building that. And then a lot of this was actually more about how do we do impact assessments, and then how do we do translation of those impact assessments for our community partners. And this is the part of the project that we were really excited to do. We had a number of really great workshops with it, but unfortunately, we don't have funding going forward with it. Okay. These are the different climate intervention strategies we were looking at. So it's across the whole suite, and these are based on existing research as well. We were trying to use a model that had these capabilities in it, but build experiments such that they would leverage those capabilities to give guidance on to what happens when you do stratospheric aerosol injections in a fully coupled system. What happens when you do marine cloud brightening? What happens when we do large-scale reforestation and afforestation? Or direct air capture? What happens with bioenergy with carbon capture and storage? And finally, this is an area that I don't really have a lot of expertise in, but we were talking about doing some ocean carbon dioxide removal as well, marine carbon dioxide removal. So looking at biomass sinking or direct taking of CO2 out of the oceans through electrochemical processes or enhanced alkalinity of changing the pH of the oceans to change the dissolved CO2 capabilities. Just quickly take you through this. This is like what we're doing in terms of afforestation. We're doing some what are called maximum feasible, and then we do politically plausible scenarios. So this one is like saying, what would happen if we took all the land that's not currently agriculture, it's not currently urban, and not currently in a protected area. So we don't want to be reforesting the Serengeti or things like that. So we were able to reforest around about 9 million square kilometers or 900 million hectares, and we were able to pull about 120 petagrams of carbon out of the atmosphere through this process alone. Sort of like there's some idea, we do these idealized ramp ups in terms of the reforestation amounts so that we can sort of start at low values and then sort of target up and wind up so that these can be achievable and they're done in the most climate positive areas. We were also looking at bioenergy with carbon capture and storage. These are things that are already in the model as well. We still have ideas about how we will go about implementing this particular function in terms of scenarios and what the fate of carbon is, but we're still sort of working on this. And then finally, looking at the stratospheric aerosol injection work, and this is work we've been doing with Walker Lee, who's who's a postdoc here, and he's been really fabulous. But the idea is if we put SO2 into the stratosphere, it will do a cascade down to sulfates and then become reflected particles in the stratosphere that reduce the amount of incoming solar. And so what we got here is the ARISE simulations, and this is Yaga's, I don't know if Yaga's here, but basically, if you put enough SO2 into the stratosphere, yeah, you can offset all that warming. Keep it this is a 1.5 degree target. But the question is, how feasible is that? How feasible is it, one, to build the planes, get the material, distribute the material? What's the life cycle of that material? And then what are the uncertainties in terms of the way we built our radiation model and our stratospheric chemistry model to give us these results? I didn't put it here, but within the ARISE project, they have the CESM model has also been involved with this, and they needed twice as much SO2 to achieve the same climate cooling. So, okay, so I'm going to finish up here. What we've got is ongoing projects that we're involved with using this particular framework for. So the first one is the CMIP7 fast track, trying to test out some of the emissions that are now coming available, some of the forcing files. This is something that Cecile and Dave have been driving. And so depending on the timelines, we could use this framework to test out those new forcing files. Scenario MIP is going to be emission driven. So here I've got, this is preliminary scenario MIP scenarios in terms of emission driven space on the left-hand panel and the expected temperature response on the right-hand panel. This is all for CMIP7. A lot of these emission-driven pathways, because they will have the interactive CO2, need to have reforestation and bioenergy with carbon capture and storage well-constrained and well-defined, because there's a real risk of misinterpreting what the scenario intentions are and the way it's implemented in the models. We've been involved in what's called the flat 10 simulations. These have been exploring an idealized emission space, so that's 10 gigatons of CO2 per year, petagrams of carbon, not CO2, per year out for 100 years, so we end up with 1,000 petagrams of carbon emitted into the atmosphere. And then we do different projections out, so in one case, we just continue on that 10 petagrams of carbon trajectory. Another one, we go to zero emissions, so we see how the model responds once you've put 1,000 petagrams of carbon in the atmosphere. And the third one does a full negative emission trajectory, so it transitions back to negative emissions and then removes all of the carbon that was actually added to the system. Finally, working with people here, we have a TIPMIP meeting in Baltimore the week before AGU. Betty and Gokhan and Aishu have been really important in leading that. TIPMIP is looking at these tipping points we were talking about. So one of the key ones is AMOC, trying to understand why does AMOC behave the way it does? Why do we get this shutdown in AMOC, and why is it so hard to restart? What are the climate implications of that? We're also looking at what happens if we have a full die-off of the Amazon in some period, or if we see a northward progression of the boreal forests. How does that change, like high latitude albedo and warming at high latitudes? Do we see temperature and climate responses for that? Finally, I'm involved in the World Climate Research Program's Climate Interventions. I'm on the Scientific Steering Committee for that, and the tipping points efforts that are going on there. And with that, I'm going to close it up. Thanks.
Okay, thank you. So we are going to open it up for questions. Just quickly, if you're online, the Slido link didn't initially appear when you brought up your YouTube page. So all you need to do is refresh, and you should see it in the description for the live video. So you can use Slido now. We do have 3 questions on Slido that came in during the course of the seminar, but we'll maybe start with a question in the room before transitioning to those. Yeah, great.
Peter, thanks for the excellent talk. You implemented this new configuration and ran for, I think it was 130 years or something like that.
Right.
You got different spatial patterns and temperature. Do you not need to go back and spin up the ocean for much longer than that, or?
It's a good call. There is a drift in the model right now. So we went from initial conditions that were in balance with that climate state. So yes, you're right. That is a perturbation, and there could be some form of longer time cycle. Yes, I agree. We're not seeing that in the analysis we're doing right now, We're not seeing drift. There could be some deeper ocean response that could re-emerge. Part of it's a practicality. I had 40 million core hours to do all of this, which sounds like a lot, but it goes quickly. And to do a longer, and I could extend the spin up on the 1850 to see if there are, emergent properties that are impacting the transient. But I guess like what we saw was that 150 years is coming off an equilibrium state that's not that different. It's not that we've massively perturbed 1850. We're cooler, yes, but that's probably going to, I don't know. It's a great question. I don't have an answer for you. Part of it's pragmatics of like, we need to get these simulations done, and we were happy with the convergence we got and the new equilibriums that we found ourselves at. ENSO statistics look good. John Fasullo has a PhD student at CU, and they've been doing a lot of analysis into fire, ENSO, trying to understand that in this new configuration. Well, the other thing I want to say, these are community runs. This is not just private, locked-off runs. If you have postdocs, if you have PhD students, or if you just want to do it yourself, these simulations are available. And I think I just lost the mic. But
It's okay, it's the ceiling's on.
okay, so what I was going to say is, if you want to get involved and do analysis with any of these simulations, the HOPE simulations, the climate intervention simulations, or just look at the historical simulations, these are available, they're sitting on Campaign Space, and they're available to the public. So if you want to get involved, please just contact me and we can help out.
Okay, thank you. So maybe bring up Sam's question real quick, is whether or not the configuration eventually will be brought into CESM proper as a supported configuration, or is it something that will be included in CSM 3? So wondering about the future of the 2.1.5 CCIS configuration.
It's a really good question. I guess Dave probably can give a better answer to that. But yeah, it's currently all in my GitHub repository. Everything is like you can access it and download it. Will we merge it back in? I don't know whether CSM 2.1.5 has new variants. I guess the large ensemble, and also if we think about the projections ensemble, that is a supported configuration. So we could do that, yeah. I'm going to go to his second. Yes, too much carbon is being emitted from the land. It's probably partly biomass, but it could be more. There's too much land use in that translation from the CMIP 6 land use trajectories historically. So I think that's an area that has a lot more to be explored to try and understand why there's so much carbon coming out of the land.
Okay, before we go to Jim's question, do we have Julio? Is that a hand? Okay.
At the beginning, you showed a plot of, I think it was aerosol differences between lens and CCIS.
Yeah. Can you just go back for it?
Over land, it was lower everywhere except over South America.
Right. That's because of the biogenics. Megan produced a lot of biogenic. We got one more, I think. So that one there.
Yeah.
Yeah. So you can see the optical aerosol depth over South America. And that basically projects out over the Pacific and also out over the Atlantic. And it's a combination of both fire and volatile organics. I haven't done the breakdown to which of those two is really the driver of that. But it's these are the same areas that people talk about for marine cloud brightening in terms of being, if you have cloud condensation nuclei, you can increase the stratocumulus dex and have a strong radiative influence to those parts. What I think is really interesting is that like these massive decreases over North Africa, India, and Australia don't have strong warming responses with them. So the question is it just that the background state is saturated, and by decreasing it, you don't really have a radiative response? Or is it the cloud regime in those areas is not sensitive to aerosols in such the way it is over the Central Pacific? And I don't have answers to this. This is, it's kind of like Pandora's box I've opened, and I can do so much understanding, but I really need people to come and help with their guidance and their analysis to be able to further explore this.
It looks like there's a source over Colombia that, is that, do you think that's the source of the plume of aerosols over the Central Pacific?
Well, this is a difference as well, right? So it's a delta between the CMIP 6 forcing files and what Megan and the fire model are putting into man. So that's an area where there are enhanced aerosols being emitted, yes. And then they project out. You can see through the central Amazon, we have less aerosols. So Megan and the fire model are producing less aerosols. I think I had unfortunately I put this figure over the top of the current day aerosols, but they actually get stronger because Megan has a strong temperature response. So as the forests warm, they emit more volatile organics, and so that aerosols over South America increases further. And you see that actually in the future projections as well. So one of the major reasons we wanted to have the fully active carbon cycle and this, so when you do reforestation, we want to know if there's an aerosol response associated with it as well. And James Weber just had a paper in Science, like maybe 3 months ago, of these simulations looking, well, actually a previous version of these simulations, looking at the aerosol driver for reforestation. So it's not just a carbon cycle, it's not just an albedo response, not just a latent heat like transpiration response. There's also a strong aerosol response going on in reforestation studies.
Okay, so, oh wow, okay. Really quick, Jim has been waiting and just submitted an online question. So given the current state of world politics, it seems that we should consider the effects of delayed enactment of positive scenarios. Presumably that's looking at SSP 119. So that is, maybe we should look at what happens if we follow SSP 370 or worse for the next 4 or 10 or 20 years. It's depressing, Jim.
Yeah.
And only then switch to a scenario such as SSP 119. So this is just about investigating maybe a more complicated scenario space. I don't know if you want to comment on that.
So, and I guess like, I can get there. It's the new CMIP 7 scenario space does have that particular scenario built into it.
I think we're going to leave that up for now.
Oh, we're going to leave that.
Oh,
Okay.
maybe not.
What I was going to just quickly show you is there is this one here. So you can see there's the, I guess it's the 1, 2, 3. The fourth one across does continue out to 2040 and then rapidly decrease. It's still a strong warming scenario, but it's basically, these are different overshoot scenarios. And you can see the temperature response on the right-hand side to those particular emission sources. So trying to explore slightly more nuanced scenarios in CMIP 7, as opposed to being sort of like just directly generated out of an integrated assessment model for a particular climate target. It's now, what's the storyline that goes with that? So it's a little bit more nuanced, but Jim, you're exactly right. We're in uncharted space right now in terms of political willingness and everything else that goes with that.
Okay, Alice?
I was wondering with the NSF project that you talked about near the start, are you or your partners pursuing other ways to try to do the interactions with the community? Because I know that, here we're encouraged to do actionable science, but usually that means partnering with someone outside who kind of a boundary spanner, and it seems a real shame that that's the part that got cut.
It really is, and Monica was totally supported by this project as well. So John and other people, thank you for filling in. So that's something we want to keep going. So we have a convergence program here at NCAR, and obviously Monica's involved with that. To me, this was actually the more exciting part. Like doing the modeling, it's like what we do, right? But it's actually applying it and making it useful to help answer questions that are being posed. I think this is we hear things from different parts of the organization and also from NSF. We've been on this climate interventions workshop for the last month, like just different sections. And they basically, NSF wants to recreate the project they just stopped funding, which is kind of interesting because one part of NSF doesn't talk to the other part of NSF. Okay, I'll just shut down.
So things are being pursued.
Yes.
Okay.
Yeah, although for as you characterize it, the boundary spanning work, which is really bringing in the community and working with them to, for example, design criteria for adequacy of model output, co-design metrics for measuring and characterizing risk. There's not currently funding for that part. Okay, I don't know who was next. Justin Small, just really quick, had more of a comment, so let's go ahead and read that out and then we'll get to the remaining questions in the room.
Yeah.
Peter, thank you for the informative talk. he noticed that the AMOC doesn't fully shut down, and I think you were talking with somebody else about this recently, but he'd be interested to run the simulations longer to see maybe what happens with respect to AMOC. So just.
Absolutely, I think it's, yeah, we would like to take these out to 2200 just to see what the longer term coupled response of the system is. That's true for the carbon cycle as well. Yeah.
Okay, so I think Keith, Isla, John, and Dave. So Keith, go for it.
The fire model,
Yes.
that's interactive.
Yes.
Is that right? So it's presumably sensitive to like precipitation or soil moisture or something like
Right,
that.
fire, weather, fuel loads,
So-
moisture in the
So are
soil.
there systematic errors in the model affecting it? So could that like source over Colombia be associated with a dry bias in that region?
Absolutely,
Right.
absolutely. I mean, the fire model has been evaluated against GFED and it does really well in terms of, I guess, global statistics and spatial patterns. But what that looks like in future projections is like completely open. We did have, initially with the fire model, issues in terms of it would kill the Amazon, so we had to spend some time doing, a lot of parameterization and trying to work out how to constrain the fire model. But maybe we've over-constrained and we're not getting enough fire in the future. We don't really know that right now. And there's a new version of the fire model, I think, Dave, that's come along for the new CSM 3 model. So we're continually trying to follow that fire line.
Okay, thank you. Isla?
The historical CO2 is impressive. Are you tuning to that historical time series?
A little bit, yes.
Okay.
Yeah. So I've done them untuned and tuned, and I actually plotted both of them. If you saw the land plots, that's the untuned version, and there is still a discrepancy between the CO2 trajectory. It's small. It's like about 12 parts per million in 2015. But yes, we did some work to try and retune 1850, and then yes, part of it was like new nitrogen fixation code that came in from CESM 6, like you guys fixed the fun bug and things like that. So, but yes, you're right. There was some tuning that went into that, just like there was tuning that went into the aerosols as well. We started off with a model that basically just got really cold really quickly when we put the raw emission factors for the fire model and the volatile organics. So, yeah.
Okay. John?
If you looked at, there was quite a lot of interesting structure and things, but both in the difference between the models and impacts and those kind of things. And I wonder whether this sort of seasonal structure of those structures.
Yes.
Have you had a bit of a look at that?
I've got all those plots and I've started looking through them.
Okay.
Yeah, part of it was to look at, is this like a northern hemisphere summer issue? Is this like more large scale ENSO? We should be probably looking, does this have different periodicity? And John's doing some work on that.
Okay.
But this is like first cut of a lot of this work.
And then the consistency between the seasonal structures between the two ensembles as well.
Yes, yeah. I think it's really valuable. And like, what I wanted to present today is still like a lot of work in progress.
Okay, Dave?
On this question about are we going to release this version, I don't know, we can think about that. But for CSM 3, part of it, what Peter didn't really say here, but a lot of this was practice to see if we can produce a CSM 3 version with a lot of these features that are turned on. So I think we learned a lot in this process, like these things that you need to do, some of these tunings. And you didn't talk about the initialization, but there's a pretty complex set of things that needs to happen in initialization. So I think there's, hopefully we're going to try to do it as we get closer to the final version of the model. I think with the CO2, one thing is important to note is there's this kink in the CO2 record, not a kink, but this flattening around the 40s. No Earth system model is getting that, as far as I'm aware. It's like a puzzle. It might be just some land use that's happening around the war. There's some other hypotheses too, some sort of natural variability. So almost no matter what, you're going to end up high because of that. The observed record flattens, and we have nothing in the model that would flatten the record. So it's kind of a...
And even in the Global Carbon Project, this is the missing amount of carbon that we don't understand.
Yeah.
That's even from like, if you do it just from inventory records, you can't actually close that gap.
Okay, do we have any additional questions in the room? I didn't see anything come in online. All right, if not, let's thank Peter again for the presentation. Okay, and I believe there's a special seminar on Friday, if I'm not mistaken, between Cass and another group, and then we do have the exchange on the 5th, and then that I think might be the end of our season till January after the holidays.
Before
you.
you leave, I want to say, you have built an amazing model. Yeah, it's incredible what CSM is. Yeah. Everyone.
Yeah.
You guys look at the airport?
Yeah.